Fine. So I'm Jaykumar from IISc. So again, I haven't timed my talk, so please let me know when my 10 minutes is up. So I'll be talking about some work that we have been doing for last 2 years at IISc in collaboration with Animesh. This is something different compared to the usual simulations that we have been discussing over here. This is something to do with kinetic simulation and based on a particle in cell code. And these are my collaborators, and Animesh is the PI for this project, and these are the funding agencies. And again, I hope you have encountered tokamak at some point, where which is a fusion reactor, and we are trying to look at how to confine plasma in a fusion reactor by applying magnetic field. That's the whole goal of this setup. And we basically work with this D3D tokamak, which is in US. This is a part of Princeton PPPL lab, and we use data from their setup in our work. So here, the basic idea is going to be that if I have a plasma which is charged and it is thermal, if you want to confine it, one method would be to apply a strong magnetic field. Then basically what happens is that these charged particles tend to, ions or electrons tend to move around the magnetic field along the field line. And then you can basically close the field line and make it into a torus, as you see over here. And what you see at the bottom over here is the magnetic field lines, right? And so they form some kind of a surface. And one of the objectives that we are going to look at is with our code that we are developing, which we call GTC-X, is to work with this particular, this is a cross section of the flux surface. And most of the codes which are available right now, there are around 5 codes in the world which can simulate this kind of setup. They work in the core region over here. This is what we call as core. And there is this black line over here, which basically represents a last closed flux surface. So outside that, you'll see that the flux surfaces don't close on themselves. And that's the region which we are interested in. The codes that are available, except for one, they mainly work in the core region. Can we extend it towards this open flux region? Right, and as I told you, we work with kinetic theory, and the equations to work with are the Vlasov equations with Maxwell's equations together. So here, if you look at it, we have this how the distribution function in the phase space, how does it evolve? That is given by the Vlasov equation, and we are considering collisionless approximation because these particles tend to move along the magnetic field line and they need not collide. It's an approximation at this stage. And the particle in cell, a short point of view is to see that we have particles which are divided into multiple cells. And the point is that we basically project these particles onto grids, as you see over here, cross sections, and then use the particles to push the particles using these set of equations which give the particle dynamics. And then once we project these particles onto these grids, we will be able to find out the potential or the electric field and use that to push the particles as well. But one of the approximation that is usually done is to take these particles as gyro averaged. You can take since the particles move around the magnetic field at a very high speed with the helical motion, you can gyro average it and consider gyro average the approximation. Again, it kind of boils down to that the 6 phase space dimensions reduces to 5 dimensions, and then we can try to simulate this particular case. And these are a set of equations you can use to simulate the particles as well as the fields. For example, over here you see how the evolution of the particle is over here, and the fields, corresponding fields, on the grid can be calculated using Poisson equation. Now, fine. So these are the set of equations we can use and solve for them. Let me present the results first. This is the actual setup from D3D, and we are kind of benchmarking our code at this stage. So we are going to work in the core region and try to test it and make sure that our results match with what is already observed in the other simulations. So here we have modeled this the core region as an annular region over here, and then we use these profiles. So these profiles typically we get it from experimental setup. We talk to these experimental guys for each of the experiments that they do. They provide us these data, and we make use of them to set up the simulation. And the one of the typical results that we look for is some kind of instability. Okay, there are multiple various instabilities that can occur, but in particular, to benchmark our code, we have been looking at ion temperature gradient based instability, wherein the temperature gradient leads to growth in the one of the modes, and we are able to extract this. Now there are other codes which can do this, right? Now what are we achieved by doing this? If you look at it, one of the main problem in implementing this code is that the field lines that you consider over here, if you have to project these particles onto these grids, you don't do or interpolation, you can't perform a simple interpolation. You need to perform this interpolation along this field line. So the geometry, the metric of the problem is not the Euclidean metric. So typically in most of the codes that are available right now, they would perform a transformation to something called Boozer coordinate, wherein these field lines. So what you see over here is opened up piece of this particular torus, and this is curved over here. But once you perform this transformation, you will get a straight line field. You can get it into straight line form, and then whenever you have a particle in between, if you have to perform interpolation or projection, you can move along these lines. So there is a simple way of implementing this. Now, if you try to do the same thing over here in the region where you're outside this domain, the last closed flux surface, this Boozer coordinate has a singularity at this point, what we call as X point. So we can't extend this further than this particular domain. So what do we do? And this is wherein we basically came up with a scheme of using a neural network to implement this. So what we managed to do is that we managed to build a neural network that would predict, given the position over here. So this is, I opened up the a torus and made it the cylinder over here. And here, given any point within the domain, I can train a neural network such that it can project this point onto the grids in one step. Typically, you can implement the same using a numerical integration scheme, which would avoid the previous Boozer coordinate, but that's very expensive. So by using a neural network, we have managed to speed up the process. So all that a neural network is doing over here is speeding up the calculation. And this is especially for a particle in cell code with millions of particles, it's a major problem to get the code running fast enough to, because the typical number of particles that we work with are of the order of hundreds of millions, right? So if you want the code to run in a few days, you need to achieve this speed up. And along the way, it turned out that instead of just performing this numerical integration along the field lines, it actually we tested it around this X point where it would fail. A typical numerical integration would fail. It turns out that it performs as good as the other region over here. So the way to interpret this is the X-axis is say the actual value, actual coordinate, and Y-axis is the predicted coordinate by the neural network over here. And you see that as long as it falls along this 45-degree line, we are good. And you find that the same thing we are able to achieve using the same neural network even in this X point region. So ideally, the same code that we have built, which works in this domain where the core region, where all the other codes work, we should, in principle, we should be able to extend it further in this domain as well. Now, the problem with this is in the community, we need to show that the code works well in the core region so that there is enough confidence that whatever results we obtain in the X region or the outside the open flux region is valid. So that's what we are working at right now. So the results that you see over here, this has been benchmarked, and again, this is an instability that is typically used to benchmark the code. And just to connect with our theme over here, the neural network is used in this particular case as a universal function approximator. And back in 60s, Arnold and Kolmogorov actually gave the background or the foundations for why a neural network or one of this form of neural network works. There is this right now popular paper in a machine learning community, which basically says how a function, multivariable function, can be approximated as a what do you say? I forget the term. Okay, as a combination of two functions, nonlinear functions, and then along these lines, there are a set of other theorems which basically prove that why a neural network works as a function approximator. So these basically work under approximations of these number of neurons over here, taking them to infinity and so on. And one of the main problem with machine learning or neural networks has been to try to come up with convergence criteria with finitely number of nodes over here. And again, this is in some sense an application of machine learning to speed up the computation of one of these simulations. I think I'll stop at this point. Yeah, thank you.
Can I ask one quick question?
Yeah.
Yeah, very nice talk. Thank you. This, on what data do you train your neural network?
So we basically have these magnetic field lines to begin with. So given this particular flux surface data, we can build, we have vectors, magnetic field vectors at each colloidal plane, and it is symmetric, cylindrically symmetric. So we can perform numerical integration to find out the, reconstruct the magnetic field line. And that is what we use to train. So it's a proxy for the numerical integration scheme. That's all we have achieved.
Hello, everybody. I'm Shaditra Dev. I'm a PhD student at IISc Bengaluru. And today I'll be talking about dynamic multiscaling in the stochastically forced Burgers turbulence. So this work was done in collaboration with Rubaitoda, who's sitting at the back, and Rahul sir, who's my PhD supervisor. So I will first begin with a brief introduction to what is dynamic multiscaling in turbulence. So in equilibrium systems, we know that near the critical point, both the correlation time and the correlation length of fluctuations diverge. And they are related to each other with the scaling ansatz, the dynamic scaling ansatz, where theta is the dynamic scaling exponent. Now in turbulence, time scales can be defined in multiple different ways. So for example, we can define a time scale as the relaxation time of the 2-point correlation of the velocity differences. And in that case, the relaxation time is related to the length scale across which we take the 2-point velocity correlation. And they also follow a power law. Now, the interesting thing in turbulence is that since turbulence is multifractal, there is not one power law exponent, but there is a full spectrum of power law exponents. So there are multiple different dynamic scaling ansatz. And each dynamic scaling ansatz has a different exponent ZP. So in this sense, turbulence exhibits dynamic multiscaling and not simple scaling. And this dynamic multiscaling has been verified earlier from the multifractal model of turbulence for different cases like passive scalar and also the Navier-Stokes turbulence. And another important thing is that this exponent ZP, this depends on the way we define the time scales. So the definition of the time scale can also change the dynamic exponent. But there is one catch in this problem. Extracting these exponents from numerical simulations is not a trivial task. Why? Because in turbulence, we have small eddies getting advected by the larger ones. So if we sit in an Eulerian reference frame and we visualize the turbulent flow, we will find that the time scale, these time scales, they scale linearly with the length scale of fluctuations. So in that case, we will get a trivial simple linear scaling. And we won't observe the the entire spectrum of the dynamic scaling exponents. So in some sense, the sweeping effects, they mask the underlying dynamic scaling, multiscaling behavior of turbulence. So what was conjectured earlier is that we can use a quasi-Lagrangian approach. So in a quasi-Lagrangian approach, we visualize the flow from the reference frame of a Lagrangian tracer particle. So in some sense, since that tracer gets advected by the flow, it somehow suppresses the sweeping effects, and one is able to observe the underlying dynamic multiscaling properties of the flow. And this has been verified from 2-dimensional and 3-dimensional simulations of the Navier-Stokes turbulence by Chamriti Shankar Rai and Luca Vifarale as well. However, such quasi-Lagrangian approaches have not been used for compressible turbulence. And there is good reason for not doing so. Why? Because a tracer particle can get trapped in a shock. And as a result, it won't be suppressing sweeping effects. And we have also verified this in our simulations of Berger's turbulence, which happens to be compressible. So the question is that, is there a way to extract the underlying dynamic multiscaling properties of compressible turbulence in such situations? So what we do is that we do the following. We load n number of tracer particles in the simulation domain, and we track the positions of the tracers as they move along with the flow. So since this is a compressible flow, the tracers will come at shocks and collide with each other. What we define over here is a Lagrangian interval. So in this picture, this is a position versus time graph of the tracer particles. So as you can see, initially they were equally spaced, and as they move forward with time, they collapse with each other. So a Lagrangian interval is defined as the region between a pair of tracer particles. So that interval is known as Lagrangian interval, and initially all the Lagrangian intervals have the same length. Now, as we move forward with time, since they collapse, we define something known as the interval collapse time, which we define as the time taken for a Lagrangian interval to collapse at a shock. And since it is a compressible flow, it is one of the most natural time scales to define in this case. So for different tracers pairs, we get different collapse times. And in that way, we get a distribution of such times. And from that distribution, we can calculate the moments to quantify the distribution. And from those moments, we can extract certain number of time scales. So this time scale, T-P-col, is the time scale which we extract from the pth moment of these interval collapse times. And in this way, we are able to observe dynamic multiscaling in, in that way, we are able to observe dynamic multiscaling in Berger's turbulence as well. So here are the results from our simulations. So this is a graph, log graph of the time scales as a function of the length scale R. So this is sort of like inside the inertial range, and these graphs are drawn for different values of P. So this is for P equal to 1, 2, 3, 4, 5, and 6. As you can see, they display quite a good power law range in this regime. And from this range, we calculate the power law exponents. So we perform a local slope analysis, and we calculate the mean values of these local slopes. The mean values give the exponents, and their standard deviations give us the error bars. So the blue and the pink points which you see over here, these are taken from two different simulations at different resolutions. And it is very, what we observe is that the different resolutions also give the same dynamic exponent. So this is not something which is like a numerical error. And the black curve we observe over here, this is our theoretical curve. This is we taken from a theory which we conjecture might be the case which is happening for such dynamic multiscaling. So I will describe the theory in brief over here. At initial time, there can be different cases depending on where we consider the tracer particles. So initially, a tracer pair might have a shock in between them, or they may not have a shock in between them. So let's look at case A, where the interval has a shock. So what happens at a later time is that this interval collapses into this shock at some time tau. In case B, when there is no shock in the interval, what might happen is that a shock might develop inside the interval at t equal to t star, and then the tracer the Lagrangian interval collapses at that shock. And similarly, there can be no shock at time t equal to 0, while one of the tracers can fall into a shock at time t equal to t star, and then the interval collapses into a shock at time t equal to tau. Now we can define the moments using this formula over here, where PR is the probability of an interval to contain a shock at t equal to 0. Okay, so let us look at the cases separately. Initially, in case A, when there is no shock inside the interval, then the velocity difference across these 2 points, that is across the interval, is independent of their separation. And the probability of finding such intervals at time t equal to 0 is linearly proportional to R. In that case, the collapse time can be defined in this manner, and then the contribution from such intervals scales as r to the power t plus 1. Now, when there is no shock inside the interval at t equal to 0, then the probability of finding such intervals is basically 1 minus r, and since r is much less than 1, this is almost independent of r. And the velocity difference across the interval at time t equal to 0 is proportional to r to the power h, where h is the scaling exponent of the velocity field. Now, there are two subcases depending on the value of t star. One is that when t star is of the order of tau, we get a scaling of this form, and then this is the contribution from such intervals which have t star of the order of tau. When t star is much less than tau, then this is the form of the collapse time which we get, and R1 can be written in this manner, where R1 is the length of the interval when the shock appears inside it. So this can be written in terms of R plus some higher order terms, and so the collapse time becomes of the order of t star plus some constant into R. And the pth moment of this time scale is all linearly proportional to R. So the total contribution from all these intervals is the weighted sum of theirs. So these are the weights WA, WB, and WB2, which are independent of R, and these are the R dependent contributions. And in the limit of R much less than 1, the leading order scaling has this kind of form, where ZP are the dynamic scaling exponents. So theoretically, we observe that this exponent is 2p by 3 for p less than or equal to 3 by 2, and this is equal to 1 for all values of p greater than 3 by 2. And this is the curve which we draw over here. So as you can see, our theoretical understanding agrees quite well with our numerical simulations. So we definitely verify that in this way, it is possible to extract dynamic multiscaling exponents into compressible turbulence. And hence, this is the summary of our work, which I have spoken about for the last 10 minutes, I think. And we we seek to extend this to higher dimensions as well, where we can observe the collapse of even more varieties of objects. For example, instead of a line, we can look at areas in 3 dimensions, volumes in 4 dimensions, and so on. And in this way, we propose a way of extracting dynamic exponents from compressible flows in general. So with that, I'd like to end my talk. Yeah, thank you.
Okay, thank you. Perfect timing. So questions?
Can I ask a question? I'm on Zoom.
Good. We hear you. Please ask it.
I missed the numerical scheme. So what kind of numerical schemes are you using for this? I missed in early part of this talk.
Okay. So we have used a pseudospectral method for simulating the velocity field in this case for our direct numerical simulations. And for tracer interpolation, we use simple linear interpolations.
So when you use the pseudospectral method, right, in Berger's equation, you form shock and the shock has to propagate, and that comes from weak solution. You have to go back to the integral equation. So how are you implementing that in the pseudospectral method?
Okay. Well, I think.
I guess you take a small viscosity.
Yes, I take a very small viscosity. Yeah, viscosity is going to 0 in that case.
So do you see the shocks propagate then after the shocks form?
Yes, the shocks propagate. Yes.
Okay. All right, thanks.
So, hi everyone. I'm Sugan, a final year PhD student working with Samriddhi. I work in the area of turbulence, and thank you for giving me this wonderful opportunity to give a short talk on my current work. So today I'll talk about the work on EDQNM MHD model, in which I'm planning to investigate the dynamo effect in various spatial dimensions. So this is a work done with Dario, Giorgio Krasnodevich at Nice, and my advisor Samriddhi here. So first, I'll just give a brief outline of the work that's going on. So the EDQNM MHD model consists of 2 different parts. One part is the EDQNM, which is actually stands for eddy damped quasi-normal Markovianization closure model for the Navier-Stokes equation. It is one of the popular closure model that people used to investigate various effects of turbulence. But unfortunately, it follows only a K41 phenomenology. It does not provide any intermittent effects. then the so-called as corrections to the K41 theory. So this was formulated in the late 70s by Khanin, Orshag, and Lee. And on the other hand, the magnetic aerodynamic equations, the problem proposed by the so-called dynamo problem is actually is basically can a magnetic field in a turbulent fluid can be sustained just from the interactions from the velocity field. So, for example, the equations in the top right as magnetic field equations, there is a diffusivity that tends to reduce the magnetic field, but also there is an interaction from the velocity field. So the dynamo problem simplifies to the question that can U, what is the properties of U that allows the magnetic field to sustain even with the presence of a viscosity. So to have a stable magnetic field is a broad question of dynamo. So Kazantsev and Krishnan has proposed a model, the Krishnan-Kazantsev model, which is a famous model for addressing this dynamo question. So in their model, it actually reduces to a Schrodinger equation in one dimensions with an effective potential that characterizes the structure function of the turbulent fluid. So what exponent does a structure function possess so that for a dynamo theory to exist? So that was a famous question, and it was solved with this model in the Krishnan-Kazantsev dynamo model. So now when combining both of these questions, so later in the 70s, Frisch, Uriel, and a lot of other people have introduced the ED-Khanin closure model for the MHD and studied the various questions in the magnetohydrodynamics part itself. And proceeding to the recent papers by Turner, Brad, Schilling, Zhu on helicity cascades and all the other effects. But till now, this was done. The ED-Khanin MHD model was investigated for integer dimensions either d equal to 2 and d equal to 3. So now the motivation to study this model is because not only that this model is a simple model that can vary over a lot of Prandtl number. Prandtl number is basically the magnetic Reynolds number, ratio of magnetic Reynolds number and the kinetic Reynolds number. So in DNS, it is very difficult to reach a very large scale of Prandtl number, but in nature, we see magnetohydrodynamic flows with large range of Prandtl numbers. So this ED-Khanin MHD model allows one to investigate such large Prandtl number situations. But apart from that, my idea is how does this dynamo action in this model change as we change the dimensions? So in this model, dimension merely acts like a parameter, real parameter, it need not be an integer one. It can change, and famous anti-dynamo theorems state that in certain dimensions and with certain symmetry, a dynamo is not possible, and we ask the same questions in our model in this same dimensions. Does the dynamo exist or do not exist? Also, one can extend this to include effects of helicity, compressibility in the rates of dynamo in this problem. Moving on, I will not go through the details, but I'll just give a rough overview of what this model consists of. For example, the equations in real space, if I show it on the top right, the spectral, take the spectral components and start taking its moments. So we know the famous closure problem that every nth moment, evolution of an nth moment will depend on n+1 moment, and this hierarchy of equation has to be closed at some point, and which is the closure problem. So for example, on the right side, the quasi-normal hypothesis, which stands for the Q and N in the ED-Khanin, assumes that the fourth order moment is actually a Gaussian, and then we can simplify it in terms of the second order moments. Also, quasi stands for the fact that we do not assume that the third moment is exactly 0. So that's a quasi-normal approximation, and carrying it over the MHD with two another assumptions that there is no cross correlation between V and B. That's the second moment between mixed moment between V and B is 0, and then the third order moment can be expressed in terms of these two moments again by the quasi-normal hypothesis. So we get the set of equations for that, and then as formulated in the original EDQNM, the quasi-normal is not sufficient for the realizability of the model. One has to introduce eddy viscosity, because we are overestimating the third order moment in the quasi-normal assumption. So we bring up Osag and Frisch has proposed this eddy time scale for both kinetic spectrum and magnetic spectrum, and introduce the eddy damping term. And the last one is the Markov initiation, which is basically we assume the model do not have memory effects, and then we assume the third order moment forgets it soon. So that's the Markovian assumption. So the final set of equations that we'll have a simplified, will look like a Lin equation in spectral space, which is shown below. So there is a time dependence, and then there is a viscous damping for the spectrum, and similarly a diffusive damping for the magnetic term. And then on the right hand side, we have these transfer terms. So these equations do obey energy conservation in the limit of viscosity and diffusivity going to equal to 0. That's a normal invariant in the MHD equations. So we assume that 0 helicity at this point. Later in the future, we intend to do it for the non-zero helicity equations also. So typically the terms of the transfer terms would look like this. This was developed for the for a d equal to 3 and d equal to 2. Now in this work we have generalized it for arbitrary d. As you can see, the d stands in the transfer term and in the geometric coefficients, which are basically b, h, and c. So just given a glimpse of what b and c looks like. The z, x, y are basically the cosines of angles formed by a triad in this nonlinear triadic interactions. So, but the take-home point is that we can see that the d clearly stands as a parameter which can be set to values between even to non-integer values. And these are the transfer terms, basically the interaction between different triads for given k. So here I have split it as a self-transfer terms, which means they interact only for the kinetic or only for the magnetic case, and interaction terms is basically how the kinetic spectrum and the magnetic spectrum interacts between themselves. So since we are looking at the dynamo, we are interested in how these interaction terms give you the dynamo rate. So moving on, in the dynamo problem, in our model, so basically, suppose if we have a stationary kinetic spectrum, if we seed in a small magnetic energy, how does the magnetic energy grow? So with our model, one can sort of arrive at this particular form of equation, assuming that the self-transfer energy is, when integrated over, it goes to 0 because it is merely interaction between different modes, and altogether they do not bring in energy. The only term that brings in energy from the fluid part, from the kinetic part, is this interaction term. And then for assuming that the magnetic spectrum is very small, we can look at the linearized one, and then one can define this dynamo rate for a arbitrary d-dimensional EDQNM MHD model. So on the right hand side, this is a famous result from a paper by Mitra, Vincent in 2019, where they have used the Khanin model, and they have extended it to arbitrary dimensions with the even compressibility factors changing. And what we see is possibility of dynamo within this parabolas, and the parabolas actually do change when we change the compressibility factors. So this was done on the basis of Khanin model. Now we are planning, the idea is to do the similar study with the EDQNM MHD model. So the different dimension EDQNM model was studied only on the purely kinetic spectrum. This is a result by Barrera and others, where they have studied the pure EDQNM model for different dimensions up to d equal to 20, and they have commented on how the K41 phenomenology changes and how the bottleneck effect arises in the larger wave numbers. As I said, this is it is at the very starting stage of our project, and the only result that I'll show here is basically, suppose if I change these dimensions from 2 to 6, even with including non-integer dimensions, just 2.2, 2.5, and then I do see that the magnetic energy on the right hand side grows almost for all d greater than 2, but for d equal to 2, as the result of which anti-dynamo theorem suggests that there cannot be a dynamo in 2 dimensions. So our model exactly, at least to this extent, it agrees with the existing result, but we intend to look closer as d is very close enough to 2. So is there a critical dimension for d between 2 and 3 where the dynamo starts to arise, or is it exactly at only at d equal to 2? And this is the spectrum, that the magnetic spectrum that we see, and as you can see, the d equal to 2 as is a decaying spectrum, and thus the value of the magnetic spectrum is very small. So as I said, our aim of this study is to look at the effect of dynamo in various dimensions, and in the future work we have to include helicity in the equation and vary that over different dimensions. And also in this dimension, just like in the Kazantsev model, we can vary the kinetic energy spectrum exponent, and keeping that as a stationary state, and analyze how the dynamo can exhibit itself as a function of varying exponent in the kinetic energy spectrum. So for the K41, we have seen that that d equal to 2 does not produce any dynamo, and we want to investigate it further. So yeah, this I'll conclude my short talk, and thank you for all your attention. I'll have questions if there are any. Thanks.
Again, so are there any questions?
Anyway, you don't expect a dynamo, right? There's a more ancient theorem which says something, I forgot.
Yes, yes, it's a Zeldovich anti-dynamo theorem says that for d equal to 2, we do not expect a dynamo to persist, or even in axisymmetrical flow, even in 3-dimensional axisymmetric flow, the dynamo cannot exist.
I mean, if there's no turbulence.
Yes.
And in this line, so why do you expect to have a critical dimension higher than 2 and not having 2 as a critical dimension?
We don't know yet. Is it because there need to be some amount of some amount of complex arrangement is needed for a dynamo to exist, and when we if it's truly because of the inverse cascade of the 2 dimensions, is this happening, or is it because of the nature of geometric terms that the model consists happens? So that's a difference that we want to study. If it's purely because of the d equal to 2 dimension, for example, the model conserves entropy strictly at d equal to 2. If it is because of that, we expect the critical dimensions to be d equal to 2 in our model. But if it's not because of the entropy construction, or if it's because of the nature of geometric quantities in the model, then it can have arbitrarily, it can depart slightly from d equal to 2.
Thank you.
I'm not sure, but yeah, that's the idea.
Thanks. Any other question? So what kind of compressibility do you want to put in the model?
The model that we have is in compressible 1, but we can incorporate compressibility by changing the by whatever relation that we want the pressure to satisfy. We will introduce a parameter between 0 to 1, saying 0 is fully incompressible and 1 is compressible. Yes.
So no coupling with the density.
No, I think no.
Okay, thank you, Sugan.
Yes, thank you very much.